Welcome to the Explainer. Today, we're putting the central processing unit under the microscope. Whether you're typing an email, swiping on your phone, or pushing your PC to the limits with a massive 3D game, there's this tiny, incredibly overworked chip making all the magic happen. It's the absolute heart of your device, and today, we're going to break down exactly how it ticks.
Think of the CPU as the digital brain of your computer. It's an absolute marvel of modern engineering. But, here's the fascinating paradox. No matter how impossibly complex your software gets, this brain's fundamental mode of operation is actually remarkably simple and repetitive. It runs on a continuous loop called the instruction cycle. Fetch, decode, and execute. That's literally it. From the second you boot up to the moment you shut down, it's just running that exact cycle millions of times a second.
And the sheer weight of responsibility on this tiny chip? It's staggering. I mean, it's not just some super-powered calculator. It's the core engine executing every single software instruction. So yes, it crunches the math, but it's also the ultimate traffic controller, seamlessly directing data between all your system's components. And on top of that, it's the security guard and the mechanic, constantly detecting faults and keeping your system from crashing.
To really grasp how it pulls all this off, here's our roadmap. First, we'll meet the digital brain. Second, we'll map out the blueprint of the processor. Third, we'll dive into infrastructure and timing. And finally, we'll walk through the instruction cycle.
All right, let's jump right into Section 1, Meet the Digital Brain.
So, here's a fun fact. Your CPU doesn't speak English, and it doesn't even inherently understand higher-level programming languages like Python or C++. Its entire worldview is limited by what we call its instruction set architecture, or ISA. You can think of the ISA as the CPU's native dictionary. It's a strictly hardwired list of very basic commands, like, add these numbers, or move this data. If an instruction isn't in that exact dictionary, the CPU is completely blind to it. It just won't compute.
And this brings us to a massive rivalry in the tech world, the two dominant ISAs. On one side, we have x86, the heavyweight champion used by Intel and AMD. It's a complex instruction set computer architecture built for the raw power you need in desktop PCs and massive enterprise servers. On the other side is ARM, which is a reduced instruction set computer. ARM is absolutely obsessed with power efficiency, which is exactly why it's the architecture keeping your smartphone alive all day long.
Moving right along to Section 2, Blueprint of the Processor.
While modern processors are staggeringly complex, if you strip them down to their absolute core, you'll find 4 specialized units working in perfect harmony. We've got the control unit acting as the brain's logic conductor, the ALU serving as the heavy-lifting computational engine, the register file providing lightning-fast immediate memory, and the LSU acting as the data bridge to the outside world. Let's take a closer look at what each one actually does.
First up is the Arithmetic Logic Unit, or ALU. This is the processor's true computational engine, and it handles 4 specific things. First, basic arithmetic, your standard addition, subtraction, multiplication, and division. Second, logical operations, handling Boolean commands like and, or, and not. Third, comparisons, literally just figuring out if one number is greater than or equal to another. And finally, shift operations, which physically slide binary bits left or right. Now, when data and instructions flow into the ALU, what comes out the other side isn't just a numerical result. The ALU also produces these crucial context signals called flags. These flags basically whisper important secrets to the processor about the result. They'll say things like, hey, the answer is 0. This is a negative number. Or, warning, an overflow just occurred because the result was way too massive to fit in memory. Right next to the ALU is the register file. Think of it this way. If your main hard drive is a distant warehouse, these registers are the chef's cutting board right in front of the CPU. They are incredibly fast, microscopic memory units for data that is being used this exact millisecond. General-purpose registers are basically scratch pads for math. Special-purpose registers have really strict jobs, like the program counter, which keeps track of exactly where we are in a program. And vector registers, those are wide, multi-lane highways that let the processor apply a single operation to a whole chunk of data at once. Our third major component is the Load Store Unit, or LSU. You can think of the LSU as the data gatekeeper. Its entire existence is dedicated to bridging the gap between those super-fast internal registers we just talked about and the much slower external main memory. It really only does 2 things. It executes load instructions, which grab data from the outside and bring it in, and store instructions, which take finished math from a register and safely write it back out to main memory. Okay, let's get into Section 3, Infrastructure and Timing.
Now, obviously, none of these specialized units can operate in a vacuum. They're wired together by a massive internal transit system made up of electrical highways known as buses. The data bus acts kind of like a cargo truck, shuttling the actual numbers around. The instruction bus carries the software commands waiting to be decoded, and the control signal bus transmits the precise orchestration commands to make sure all the hardware fires exactly when it's supposed to.
And when we talk about hardware firing, we really need to pause and talk about sheer mind-bending speed. 1 billion. That is what a single gigahertz represents. So when you buy a laptop and it boasts a clock speed of 3 gigahertz, it means the processing cycles we're talking about are happening 3 billion times every single second. It's a scale of speed that's honestly almost impossible for the human brain to fully comprehend.
To keep those billions of cycles organized and prevent total chaos, the processor relies on a conductor and a metronome. The control unit acts as the conductor, managing the logic and the flow of instructions, but it dances strictly to the beat of the system clock, our metronome. The clock generates a continuous series of timed electrical pulses. Every single CPU action is synchronized perfectly to these microscopic, relentless ticks.
Which brings us to our final part, Section 4, the instruction cycle.
Now it's time to put it all together. Driven by that continuous, relentless pulse we just mentioned, the processor handles your software through a classic 5-stage pipeline: fetch, decode, execute, memory, and write back. Let's slow time way down and walk through one single microscopic cycle to see exactly how software code turns into physical reality.
Stage 1 is the fetch stage, where the processor needs its next order. First, the control unit checks the program counter to find the exact memory address of the next instruction. It reaches out to external memory, physically retrieves that instruction, and loads it directly into its instruction register. And crucially, the program counter instantly ticks up by 1, so it's already pointing to the correct address for the next cycle.
With the raw command now inside the chip, we hit Stage 2, Decode. Here, the control unit acts as a master decryptor. Imagine the raw code says add R1, R2. The control unit breaks it all apart. It sees the operation code add and instantly wakes up the addition hardware. It sees the operands R1 and R2, identifying exactly which registers hold the numbers we need. It translates all of this into synchronized electrical signals, prepping the whole chip for action.
Then we get to Stage 3, which is where the magic really happens: execute. Depending on what was just decoded, the control unit acts like a giant switchboard. If it's math, it routes signals right to the ALU to crunch the numbers. If it's moving data, it signals the load store unit. Or, if it's a conditional jump, like an if-then statement in a video game, it actually rewrites the program counter to a totally new address, instantly changing the direction of the entire program. Finally, we hit the conditional wrap-up, Stage 4, memory, and Stage 5, write back. Now, these only trigger if the specific instruction demands it. If data needs to be pulled from or pushed out to the main computer memory, the LSU takes care of it right here in Stage 4. Stage 5 is just the final cleanup. The processor takes the shiny new computer result from the ALU and tucks it safely away into an internal register. Cycle complete. Time for the next one.
And that cycle right there is the invisible heartbeat of the modern world. A modern processor truly is a flawless orchestration of billions of microscopic pulses every single second. By dividing the labor among these brilliant architectural units, the control unit, the ALU, the LSU, and the registers, and forcing them to march to the rigid tempo of the system clock, the CPU seamlessly turns simple electrical states into the vast digital reality we live in.
Which leaves us with this final thought as we wrap up today's explainer. You're likely watching or listening to this on a device right now. So how does it change your perspective knowing that every pixel on your screen, every sound in your headphones, and your entire digital experience at this very second is built entirely on the unseen, flawless orchestration of billions of microscopic electrical pulses? It's a true miracle of modern engineering. Keep that in mind the next time you boot up. Until next time, stay curious and keep learning.